Hello everyone, welcome back to the channel. In this video, we're going to show you how to solve complex algebra problems without using derivatives, calculus, or long equations. By translating algebra into geometry, the solutions often become surprisingly simple. For example, the shortest distance between 2 points is a straight line. The square of a positive number can be viewed as the area of a square whose side length is that number. When you think visually, the math becomes intuitive. What you will learn: how to reinterpret algebraic expressions as geometric vectors, the unfolding method, why visualizing is often faster and clearer than calculating. Let's walk through the problems one by one. The first problem is this. Given two positive numbers x and y such that x plus y is equal to 12, find the minimum value of the expression. The square root of the square of x plus 4 plus the square root of the square of y plus 9. At first glance, this looks like a purely algebraic problem, and yes, you can solve it using standard algebraic methods. However, if we approach it geometrically, the solution becomes far more intuitive. Let's take a look. From the structure of the two square root terms, we can interpret each as the hypotenuse of a right triangle. The first triangle has legs x and 2. The second triangle has legs y and 3. Now imagine placing these two right triangles as shown on the screen. The legs x and y lie on the same straight line and meet at point P. Their hypotenuses also connect at P, forming a broken path from point A to B, passing through P. This means the value of our expression is exactly the length of the path A to P, then to B. But we know a fundamental geometric fact. The shortest path between 2 points is a straight line. Therefore, the minimum value of the expression is simply the straight line distance from A to B. When we connect A and B directly, we form a new right triangle whose vertical leg has length 5, that is, 2 plus 3, and whose horizontal leg has length 12, since x plus y equals 12. Applying the Pythagorean theorem, AB is equal to the square root of the square of 5 plus the square root of 12, then, equal to the square root of 25 plus 144, finally, equals 13. So, the minimum value of the given expression is 13. The second problem is similar to the first one, but now we are given three positive numbers x, y, and z. Our goal is to find the minimum value of an expression involving three square root terms, each depending on x, y, and z, as shown on the screen. From the structure of these terms, we can once again interpret each as the hypotenuse of a right triangle. The first triangle has legs x and 1. The second triangle has legs y and 2. The third triangle has legs z and 3. Now imagine placing these three right triangles together as shown on the screen. Their hypotenuses connect in sequence at points B and C, forming a broken path from A to B, to C, and finally to D. As addressed in the first problem, we know a fundamental geometric fact. The shortest path between 2 points is a straight line. Therefore, the minimum value of the expression is simply the straight line distance from A to D. When we connect A and D directly, we form a new right triangle ADE. Its vertical leg has length 6, from adding 1 plus 2 plus 3, and its horizontal leg has length 8, because x plus y plus z is equal to 8. Applying the Pythagorean theorem, AD equals the square root of the square of 6 plus the square of 8, then equals the square root of 36 plus 64. Finally, the square root of 100 equals 10. Therefore, the minimum value of the given expression is 10. When does this minimum occur? The minimum occurs when the vectors are collinear, forming a single straight line. This means the slopes of the three individual triangles must be equal. 1 over x equals 2 over y and equals 3 over z. Using properties of ratios, this equals adding 1, 2, 3 over adding x, y and z is equal to 3 over 4. That is, the line's slope is 3 over 4. Using this slope, we can find the specific values of x, y, z. x is equal to 4 over 3, y equals 8 over 3, and z is equal to 4. Adding all of them result in the checksum of 8. That is correct. As you can see, finding the minimum value in these problems is, actually, a direct application of the Minkowski inequality, as shown on the screen. However, it's important to note that the geometric, straight line principle we used provides an intuitive, visual proof of this inequality. In other words, the geometry doesn't just illustrate the result, it proves Minkowski's inequality in a simple and elegant way. The third problem asks us to find the maximum value of a sum, involving two square root expressions, each depending on the same variable x. From the structure of these square root terms, we can once again interpret them as the two legs of a right triangle. By the Pythagorean theorem, the hypotenuse of this triangle is a constant value of 2. This means the three vertices A, B, and C of the triangle lie on a circle, whose diameter is AC, the fixed hypotenuse. Now extend a line from A through B, and mark point D such that BD equals BC, then connect C to D. This construction creates a new isosceles right triangle. In this setup, the length dA represents the value of our expression. So the problem reduces to finding the maximum possible length of dA. As point B moves along the circle, the point D moves as well, causing the length dA to vary, from dA to EA. However, one key fact remains unchanged: the angle stays at 45 degrees. Then, what is the longest length? Using the law of sines, we find that the length dA depends on the sine of angle DCA. It becomes clear that dA reaches its maximum when angle DCA is a right angle. In that case, triangle DAC becomes an isosceles right triangle. Therefore, the maximum possible length of dA is 2 times the square root of 2. The last problem is this. Given x equals the square of 98 plus the square of 99, find the value of the square root of 2x plus 1. The expression for x contains two squared numbers. We can interpret each square as the area of a geometric square. One square with side length 98. Another square with side length 99. So the value of x is simply the sum of the areas of these two squares. By placing the two squares side by side, we can clearly see the 1 unit difference between their side lengths. Then 2x represents the total area of two squares with side length 98 and two squares with side length 99. If we arrange these four squares side by side, as shown on the screen, they form a larger square whose side length is 98 plus 99. The area of this new, big, square is equal to the combined area of the four smaller squares, which is 2x, minus the area of a small missing square of side length 1. Thus 2x minus 1 is exactly equal to the area of this larger square, whose side length is 98 plus 99. Therefore, the square root of 2x minus 1 equals 98 plus 99, in total equals 197. In summary, we explored 4 problems that demonstrate how to solve complex algebraic expressions, without relying on derivatives, calculus, or lengthy equations. By translating algebra into geometry, the solutions become surprisingly simple and intuitive. We use several key geometric insights. The shortest distance between 2 points is a straight line. The square of a positive number can be interpreted as the area of a square with that number as its side length. Constructing right triangles and geometric configurations can reveal maximum or minimum values instantly. When you think visually, the math becomes intuitive. What you learned: how to reinterpret algebraic expressions as geometric vectors. The unfolding method. Why visualizing is often faster and clearer than calculating. Alright, it's time to wrap up. What did you think of the problems and the solutions? Leave a comment below, and don't forget to like, share, and subscribe for more fun math problems. See you next time, and thank you for watching.